Go ahead.
Okay, welcome everyone to HAO Colloquium. Today, our speaker is Pratik Mayank from Space Weather Trek. It is my great pleasure to introduce Pratik. Pratik completed his PhD at the Indian Institute of Technology, Indore, India, supported by the prestigious Prime Minister's Research Fellowship. During his PhD, Pratik developed the Swasti framework, an MHD-based solar wind and CME model. After his PhD, Pratik joined Space Weather Trek as a NASA JAC postdoctoral fellow with Enrico Camporiel. His current research focuses on enhancing physics-based space weather forecasting models through AIML approaches. Today, Pratik will be speaking on neural enhancement of the traditional WSA solar wind relation.
Thank you for a nice introduction. Is it okay if I stand?
Yes, whatever.
Okay. Yeah, hi everyone. So thank you for giving me this opportunity to present and achieve. This is the first time I have been here officially. As you can see, I will be talking about an alternate of the famous WSA relation or model. And so these are the funding agencies, these are the affiliation, and these are the collaborators. Zengon and Givertoth have been involved in something else as well towards next generation solar wind model, hence their name. So I forgot about the introduction, so I made some introductory slides as well. So I did PhD from IIT Indore. This is the building in which I was working. It's a very weird building. This was my group. I mainly worked in the MHD simulation using Pluto code. It's an astrophysical code for the MHD solutions developed in Italy. It's very widely used in Europe, especially. And I also used Python, like everyone. The main outputs were Swasti, SolarWind, Swasti CME. These are MHD SolarWind models, just like Enlil, Euphoria, these things, WSA and plus MHD. I also worked on CME interaction, and the goal was the space weather drivers. Then in postdoc, we wrote proposal to use deep learning to get over some of the challenges that we have in this pipeline of SolarWind and CME. So now I'm doing machine learning surrogates, now PyTorch, and the WSA Plus, which has been developed, and I will be talking about that only. And the overarching goal is to have next generation SolarWind models. So I will talk about that slightly. And in AGU, I will be giving talk on WSA Plus, the similar talk on Friday late morning before lunch. And the MHD surrogate, which I will briefly touch upon, maybe not, will be on early morning on Monday. Okay, so coming back to the technical part. So before going to next generation, let me briefly summarize the current modeling approaches of solar wind. And we all know why solar wind is important. It's a background in the heliosphere. So anything that propagates in between sun and earth will be impacted by the solar wind conditions. So we need to find what is the current ambient conditions. Even those are recipes, because connectivity is also coming from solar wind. If we want to have any study from the solar atmosphere connecting with the in situ observations, we need to have good estimation of the solar wind, because that's the field lines we need. So for this, currently we have majorly three approaches. First is the full physics-based 3D MHD approach that takes input, let's say at anywhere, mainly at 0.1 AU, and then solves the MHD equations and provides the 3D magnetic field velocity, density, pressure, everything, like Enlil, Euphoria, Swasti. Some of the models also have MHD in kernel, which I will come to it later. But in this 0.1 to 1 AU, which is the part from which the solar wind becomes super alphanic, so it becomes a little bit easier to solve the MHD equations for solar wind, because everything is propagating radially outward, nothing is coming back. So in Enlil, Euphoria, Swasti, many things are there, and the only disadvantage is that it takes large amount of time and computational power. So at least more than 200 CPU hours is required to solve for one state or even for steady state solution. Then we have empirical or semi-empirical models like Huxley, which take again just solves in 2D extrapolation using crude approximations of the main physics. And the best part is that it only provides a speed, nothing else, but this speed matches with the MHD. Almost the similar accuracy is there. And runtime is few CPU minutes, maybe seconds. And then we have machine learning, which is becoming more and more popular. We have a bunch of papers, but most of them are using the magnetogram or solar surface observation and only providing the displays, 1 AU around observations. Not 2D, not 3D, nothing else, just 1D speed profile mainly, and takes few seconds. The difference can be seen as the trade-off between physics and speed. If you want better physics, we have to give more time or computational power. If we go to the machine learning approaches, which acts mainly as the black box, then we have higher amount of speed. In the coronal region, which acts as the initial conditions for the heliospheric, we have both WSA, which is semi-empirical, and MHD. So like MASS, Awesome, they do MHD simulations in those regions as well. And then we have WSA and similar little bit variant of those. The important part is that if we use the boundary condition either from WSA or MHD, we get similar accuracy at 1 AU. And there are also tunable parameters in MHD simulations in the corona because of many regions, transition region, and all those things. So again, that is also tunable. So we need to have iterations and the best fit will go into the simulation. And that's how everyone is doing it currently. So both are tunable, but the MHD is physics-based. So the point is that if you are tuning, the WSA is much faster. And in the operational forecasting purpose, this MHD takes a lot of time on corona. So the best approach, which all the operational forecasting models are using, is WSA plus MHD, like in before you, yeah.
Let me ask a clarification. You said at about 0.1 AU, the solar wind becomes super alphenic. It's already supersonic from very low end, but at that point it becomes super alphenic, meaning that even magnetic waves and magnetic information cannot travel back.
Yes.
It's all forward. So
Yeah.
that's why these empirical models are usually cut off.
Yes.
Start. The MHD starts there.
Yeah. Yeah.
Okay.
And so it's not rigidly 0.1 AU, it's
Yeah.
15, 20. So 0.1 AU is 21.5 solar radius, but that's the value which makes it 0.1 good enough looking round number, as well as we are ensuring that we are beyond that point. So it will be inside it, not outside. If anybody wants, it can take 20 solar radius or 18. People take it. Many people can take. Some people also take 5 solar radius. So now they have to defend themselves why they are taking 5, because their model should be incorporating the back propagations as well. So that's it. So yeah, so the current operational forecasting, which is Enlil in SWIPSI, Euphoria in Europe, and Enlil again in UK Met Office, they take WSA and MHD. And obviously HAX is there and machine learning are there. What we are proposing as the next generation approach is that replace WSA with something called WSA Plus and have surrogate models for MHD. That it will take the input as any other MHD model and will provide all the 8 parameters, properties in 3D in just seconds. So that's the goal. So that it's the full pipeline is fast as well as reliable. By reliable, I mean that it should be physically good enough accurate as well as some uncertainty bound to it. So the current state is that WSA Plus is ready. It's published now recently, but MHD surrogate is under development. And I will be mainly talking about the WSA Plus. So before diving deep into this, how we develop this WSA Plus, which is claimed to be much better than WSA, on average 40% better, which is, I think, a good number. So this is the WSA equation. If you don't know, it's a basically equation between the velocity that we get at 0.1 AU as the input for the MHD solution, based on these two observations or observationally derived parameters like expansion factor and minimum angular distance of the field line from the coronal boundary. So it's a very weird looking equation, inversely proportional to expansion factor and directly proportional to this, how deep inside the field line is originating. These orange alphabets or numbers are basically the independent parameters. We don't know their value. We need to tune it and then get the value, the best result out of it. From large long-term studies, we have kind of got this average or default value. If we take these values, more or less on average, each time you will get decent accuracy. But it doesn't mean it's the best that this relation can do. You can take much better result out of it using different values. But for forecasting, we don't know which value to use. So just to explain, so this is an observation that we get in situ speed of the solar wind. If we use default WSA for forecasting of this duration, with those values, we'll end up getting this. This is the speed from the WSA. WSA plus HUX extrapolation and this in situ speed. But if we use this observation, then tune those independent parameters, then we can get this. So the relation has that capacity to give much better results. But because of default values, we don't know which values to take. There are so many independent parameters. We end up getting this if default values are used. With WSA plus, we are trying to kind of generalize the optimization of these independent parameters. And this is what we get from WSA. But this is for forecasting. The orange line is when we don't know what are the observations. Those are not optimized. Those are the default setup. So now let me show you how we have done this. And that was the representative case. More or less in every case, the status is similar. So these are the two things, expansion factor and minimum angular distance. And please stop me anywhere if I'm not clear. Since we are a small number of people, we can even make it more like discussion based. So two things are required for WSA is the expansion factor and minimum angular distance. So we take the synoptic magnetogram, then solve or do the extrapolation of field line using PFSS. And then we end up getting an estimate of the coronal hole as well as the closed field lines. So by coronal hole, I mean open field lines. So these green are the open field lines and these gray and grayish type are the closed field lines, plus and minus. And these are the foot points, these red dots, from which the field lines are originating and reaching to the Earth. So it's a projected view. These are the Earth's sub-Earth latitudes. So those field lines are originating and then coming like this. So this is the projected view of that. So from there we have the expansion factor and minimum distance. So it depends on BR. We take a source surface. We have BR at 2.5 or any values. And then we make expansion factor, minimum distance maps. And these are the open close coronal hole regions. So the basic assumption is that all the solar wind are coming from coronal holes, only open field lines, nothing else. And this is the WSA speed, the default one. Now, this is the pipeline, which is clear. Take the magnetogram, have the expansion factor and minimum distance maps, 2D, 2 maps, then do something instead of WSA and get the speed profile. So replace the equation with neural network. That's the basic idea. And as compared to all the other approaches, we have this additional step, which provides interpretability to this whole pipeline. Now we know how the machine learning is kind of, or what are the connections that the neural network is looking for. So they are relying on expansion factor and MAG, not the magnetogram. They are not figuring out what to look. We are providing what to look. So that's provide the interpretability and it makes it more like WSA pipeline. Then the question is that what would be the reference, the target that we take and tell the model to learn this. This is the input and this should be the output. So now you figure out and give us very good results. So we have output, that is the in situ solar wind observations. But the problem is they are 1D. They're not 2D. They are just 1 point. But we want full 2D input so that it can act as the input for 3D MHD simulation. So this is a big problem. So there is inconsistency in the nature of this, that the target or the observations that we have and the output that we want. So that's the biggest hurdle in this approach. And the first approach that we took was quite intuitive one. I take two maps, take 1D in situ, means take these two maps, extrapolate with HAX, and whatever the result we have, just put a loss for sub-Earth points. Forget 2D, just consider sub-Earth points, and expect that the neural network will influence the full 2D map based on that. That's one approach, it might work. And the second approach was, again, take 2D maps. Now, instead of just relying on 2D maps, find the best fit for the independent parameters, not for 2D map. Just solve for sub-Earth points, take Omni data, and what are those best optimized WSA maps. And then take a stack of these optimized maps and then try to generalize it. So we are kind of optimizing the generalization of WSA. So we tried with the first approach first, and it led to overfitting at sub-Earth points. So if we do in that case, these sub-Earth points will look totally different from these. The model tries to overfit those sub-Earth points and looks very bad and inorganic and physical. Then we tried this second thing, and we got a hit that the model was successfully able to generalize the optimization. So if I go to maybe this, so this is the optimization one. We are trying to generalize this optimization, not based on the equations, just through the maps that we get from this optimization. And that's is this one. Okay. I hope some part is clear. I have got the feedback that most of the time it's very complicated. I don't know I'm able to explain it or not, but let me try with this flowchart. So we have synoptic magnetogram, just BR at the solar surface. Then we use PFSs to extrapolate the field lines. From there, we have expansion factor and mean angular distance 2D maps. And those acts as the input for everything. These two maps are the main thing, not the synoptic magnetogram. Now we take the traditional WSA equation, use LBFGS scheme for optimization of these independent parameters. And we have almost 14 years of data, 14 years of map optimized based on the observation. No forecasting, nothing involved. Just optimize WSA for 14 years and keep a stack of those maps. Now use those maps as the input for a neural network, swing transformer, mainly for vision 2D maps and those things. Shifted window transformer is called. And these inputs, these maps acts as the input for swing transformer, and its goal is to just find a generalized relation that whatever input I provide, you give me the optimized WSA at every time. So this is coming from this extra step, and the ground truth becomes this optimized map. And then we compare with the observation to see that how good we are there. But our ground truth will be the optimized WSA maps, not Omni data, which is just 1D. But now these optimized 2D maps are 2D. So now we have 2D output and 2D loss. So that's the main idea here. After the learning, after successful, assuming a successful learning, so these are few trends that I would like to talk about. This is the default WSA with the default set of values, which is used for forecasting. Then we optimized using observation. Then we get this, which looks slightly different, but only for the sub-Earth latitudes, these are been optimized. Now, if we try to generalize this pattern, we get this, which is WSA plus. So you can see, especially if you look into the solar minima, while it was trying to optimize for sub-Earth points, it is giving around 400 or 500 speed at the polar regions. And we know this is kind of, it can be possible, but rarely. It's not a usual thing. And it is never like that. So here it is around 600, but here around 450, 500. So it is very clear that just to get the optimized fit for these sub-Earth points, it has fitted for this polar regions as well. So the polar region should be 700, 800, but it is giving 500. But when we take a stack of all these images and try to generalize it, then you can see it is giving the high speed. Because the model is seeing that in most of the cases, at the polar regions, the speeds are very high. So in general solution, it should also be high. Now, if we compare these all three, these are the values. So it is more correlated to this WSA plus for this around maxima case and more related to this in the minima case. So the basic understanding is that even if you optimize through the normal ways, we can overfit or have a wrong 2D map. That can be possible, and we are seeing it here. If you do MHD simulation of this and the CME is going around here in the higher polar regions, our solutions can be very wrong. Now, comparing with the observations, it is not trained on Omni data, it is trained on optimized WSA maps. But for testing, we can compare with the Omni data. This is at 21.5, then extrapolated to 1 AU. So again, same color combination. Green is for the optimized, that we optimize the WSA relation using observation. Blue is the default, and orange is WSA plus. So you can see it is much closer to green. Obviously, it should be, that is the target. But the only caveat here is that you can see it is slightly more smooth. It is lacking those sharp jiggling effects. Here you can see it is smoother. And when we extrapolate to 1 AU, and you can see the similar situation. This was also the case. In the heliospheric ecliptic plane, you can see that the variations of the kind of features remains the same. Their values are slightly different. If the values are different, they can have different drag on CME. SIR strength can increase or decrease. Those things can happen. Now, for all those data for 14 years, we have compared with the Omni WSA plus, which is ready for forecasting and nothing is required, and the WSA default, which is used for forecasting. So you can see there is this gap. This is the average value, and these are the scatter points. And if you try to fit it, then this wavy pattern is kind of visible. So you can see this almost fit score, which is based on these four: RMSE, mean absolute error, dynamic time warping, and PCC. If we use all these four and take the normalized value, that's what we are calling fit score, because we only knew these standard matrices and that's what we had. So we made a score out of it. That is called the fit score, and that's around 40% better. So that's why we are calling it 40% better. For dynamic time warping, which I think is one of the best metric to compare two time series, that is around 60%. The RMSE is 40 and MA is 45, but the PCC remains around 0, that is 1, because inherently the features remains the same. The values are kind of changing. So PCC is just a linear thing, so it remains there. And this is the average value, not for a specific case. So overall, the features are same. Now coming to the solar cycle activity behavior that we have seen, this is the solar cycle sunspot number, and this is the behavior with Omni of the WSA plus. So we are seeing a shift in the minima and the maxima. So it's not like the model or the WSA pipeline is performing bad in solar maxima. But I have been told that instead of plotting solar sunspot number, maybe we can try with the this polar field strength, because that is slightly shifted. So that we have to check. So if that matches with the peak of this minimum, then there can be some kind of feature mapping. But right now it seems very weird. In the declining phase, the performance is bad, and it's only 1.5 solar cycle. So nothing can be kind of concluded here. So we have made a Python package out of it. It's called WSA Plus. It's fully open source. All the codes, all the data set, trainings, everything is, whatever I wrote, it's there. And it's very easy. Pip install WSA Plus. All we have to do is just provide a synoptic magnetogram if we provide the map. And then you can figure out what to do, whether you want HUX or anything, or MHD simulation from it. It's published. You can read the paper. If you want to uptake the work, we can collaborate or something like that. So after this, say WSA Plus is ready. Obviously, there are a lot of improvement that can be done here. And the sharpness can be increased, the architecture can be increased, a lot of things can be done. But currently, it is providing on average 40% improvement with respect to the existing WSA as the boundary condition for all the MHD simulation models. And it's not only about the solar wind, as I said, solar wind is the background. So even if you want correct CME simulation, we kind of focus more on WSA plus as compared to the WSA. Talking slightly about the surrogate model, which is, I think, little more ambitious project. It is taking a lot of time as compared to WSA plus. So the argument is simple. We have this map. Obviously, we assume kinetic energy conservation. From there, we have density plot. We are extrapolating. So we have B5, B theta is assumed to be 0, and then constant pressure. So from this, we get all the initial properties. That's how everything is done. Otherwise, use MHD. So if we go through this pipeline, we have WSA plus now. We can use other properties deduced from this. Then they act as the input. 2D spherical shell acts as the input. And this physics-informed neural operator provides 3D plasma, 3D output of all the 8 properties. The goal is to introduce partial differential equation loss, PD losses, all the MHD equations, and the data loss as well. For data loss, we have collaborated with the Michigan people. They have given us awesome simulation, 100 CRs, in which 88 was good, so we have taken 88. Then obviously these B and V vectors and pressure and rho. Then we take these 2D, lift it into 3D, try to learn everything in Fourier space, not in the real space. And this is a very simplistic explanation of the system that we are trying to do. We have slightly deviated from this as well. So the bottom line is that we take these inputs and provide these 3D profiles from 20 solar radius to 250 solar radius. These are very initial results, and I think this was the first attempt that we did. We are trying something else right now, but hopefully we'll have very similar results. So this is trained on very limited data set, and this is from the training set, not from the testing set. So you can see that the model is learning very nicely. This is the density profile, this is pressure, this is a speed, slightly deviating at these regions at low values, and this BR. Things are different now. BR is matching very nicely, and now we are struggling in density. But hopefully this is the case that we are kind of struggling with the final setup that we kindly focus on. Again, density, that was the ecliptic plane. Now we are in the meridional plane. You can see all these structures, even like these regions, are very captured very nicely. So this is full 3D. So you have this ecliptic plane, and this is meridional plane. You have everything. And you can see in meridional plane, slightly easier for the model, because ecliptic plane has more dynamic thing going on. Okay, so more about the MHD surrogate in AGU. So just to summarize this, we have WSA plus now, which is claimed to be 40% better as compared to WSA plus, and it can be used very easily using pip install WSA plus. The MHD surrogate is under development, and the goal is to provide MHD simulation in seconds. This is only for the solar wind now, right now. There is no CME. So there is no time evolution of the input condition. Input condition remains the same, and it enforces the steady state solution. Similar thing can be extended to other PD systems as well, because the focus is to have MHD solver, not the solar wind solver. So we are trying to develop the MHD operator surrogate, not the just solar wind. So similar feature can be extended to anything. So the idea is to incorporate CME as well, but if we have different domain, same thing can be extended very easily. Because MHD are hyperbolic equations, they are one of the most challenging ones. So Sun-Earth connection, that is the main goal. So we will have full differential pipeline from the solar surface till Earth. By fully differentiable pipeline, we have the advantage that we can tune it. If we are missing physics or missing any information, even then we can match with the observation. That is the biggest strength. Then obviously we can take multi-vantage point observations, and those things can be tested. So yeah, that's it. Thank you for giving your time.
Thank you. questions?
When you go in WSA, you're trying to optimize it, are you using the adapt maps or are you you're using just Gong maps?
Gong.
The adapt ones, okay.
Yeah.
Yes, I also have a question about that. Why do you use Gong map? It's much poorer resolution. Do you need that?
So I think the resolution of adapt and gong is same, right? Because adapt is taking gong. So the resolution remains the same. The main reason is that the gong map has the large amount of data for 14 years. And yes, and 0 point corrected is there, integrated current and rotation map is there. So the adapt maps also have those, but those are not open source. I think the Air Force develop for themselves. I don't know. So I will have to collaborate with adapt. The main reason was the data set, 14 years. Resolution is fine. I think adapt does have sinusoidal spacing or not. I don't know. Means every other reason is fine. So the same thing can be done with adapt. No problem. The main reason was
That just gives you a more accurate far side.
yeah,
Which makes your
far side.
synoptic map a little
Yeah.
bit more accurate. It still doesn't have emergences or anything in it, so it can miss quite a bit during, especially during maximum, but it's slightly better on the far side.
Mhm.
So WSA outputs both the speed and the IMF polarity, and sometimes, they can get the IMF polarity quite wrong. Do you also consider that while you're tuning WSA for the pipeline? Or do you only consider the radial speed? Or
Just the radial speed right now. Yeah. Because means WSA designed only for speed. It's an empirical relation for speed. Yeah, it can. As far as polarity is concerned, the polarity mainly, if we go through this approach, mainly comes from the extrapolation of field line from PFSS and SCS. WSA itself doesn't provide any polarity. So if there is a problem in polarity, it's because of PFSS and SCS, not because of WSA. Mainly.
SCS is the Shatton current.
Just current current sheet.
It's another model for this.
The model, but which is actually not very much required because the deviation is less than 1 degree and most of the resolution in these cases is 1 degree. So even if you skip it, it's beyond like inside the error bar.
I have a question about the final WSA optimized you showed still has a fairly smooth solution compared to the, if you pull up one of those plots like this one. So that
Lot of animations. Yeah, this one.
yeah. So
Are you saying that why is this coming?
WSA plus, I'm sorry, has the smoother solution to, if you optimize WSA, you still capture those spikes in speed, of course, because you're just sort of bumping up the WSA solution. Yeah, and then WSA plus has this smoother solution, which like if you look at the around 170 there's a pretty large spike in speed, which WSA plus doesn't capture.
Like these?
Yeah.
Yeah.
What's causing that, and how would you go about perhaps mitigating that? Because those are the from a space weather standpoint, those are the ones you want to get right. Those are the high speed streams you really want to predict both in time and speed most accurately as possible.
From our understanding, what we have came to the reason why is this happening is that the way it is being trained is on 1 hour data set. So, and HUX is more diffusive as compared to other sharper things. So even if we take this as obviously if we take this, it will come to this one. Even if we increase the sharpness of the orange line, it will end up almost having this. If we extrapolate with HUX with 1 degree observation, 1 hour cadence will be Omni. So the bottom line is that this sharpness is actually kind of not being caught because of the training pipeline. 1 hour cadence plus HUX is making it diffusive. So model is not giving importance to these sharp features because the loss is not arranged in such a manner that it respects those sharp features. So the next idea is to try RK4 instead of HUX. Maybe that can be more, or that can be better in kind of having those surfaces till 1A.
RK4 is a run good.
For simple extrapolation scheme, but instead of HUX, we can do that.
Okay.
So Enrico and Andong has seen that RK4 can be much more better as compared to HUX, or less diffusing than HUX. Another is 1 hour cadence. If we go to higher cadence, then it will be better, I think. Yeah. But again, the magnetogram is also from there. So yeah, I think if you replace HUX with RK4, it will be slightly better. And I think that's fine, because our main goal is to attain this. But obviously, if this acts as the input for MHD simulation, this also should be good enough.
What do you mean it should be good enough? I mean, if you miss those big spikes,
Yeah.
isn't your MHD solution
Yeah.
going to have a similar
Yes.
miss of the?
Yes. So that's the point, that if we miss this, we are missing near sun conditions, not great at those places, even though if we match at 1. So we want to have this as well, as good as possible.
All about choosing the right metric, right? I mean, if you look at that blue line down there, that's underestimating the overall value and that, but it actually has an increase that's coming up. It's phase shifted. Maybe like an RMSE error metric versus a weighted thing for the spike, which is the important feature for the space weather perspective. When are these CIRs going to happen? When's the CME thing going to happen? That's the thing there. We did a whole bunch of stuff on this back in the SISM era about trying to figure out the right metrics for that
Yes.
calculation.
So do you think if we want to compare 2 time series plot, any time series plot, so what's the best metric?
Well, you can't answer that question, right? It depends on what you want to do, right? I mean, if you want to capture those spike features, you need to use something other than an RMSE kind of error metric. We were using one that was doing a thresholding, looking for capturing thresholds and spikes, because that's the important feature that matters for the space weather prediction. Can I ask a really dumb question? Can you go back maybe 1 slide? And 1 more. Yeah, right here. So on this the bottom thing, right? You got, those images that are inputs, which are, I think your expansion factors and your distance from the open closed boundary, right? Those are just sort of images. Why don't you treat it, or why can't you treat it as an image generation problem of how do you create a neural network that takes those images and transforms them into the image to the right? Just treat it as an image thing, right? How do I make horses into zebras or something like that, as opposed to trying to do a more traditional network? Or maybe I'm misinterpreting what's going on here.
So if I have understood clearly, you are saying that provide these inputs,
Right.
and ask the network to learn this output.
Right. You try to.
But we don't have this. That's the problem. We only have in situ time series 1D. We don't have 2D. So if you want to make 2D,
Where did that come from?
so this came from the optimization. So we have observation as 1D, right? So what we can do is extrapolate for sub-Earth points and then tune your independent parameters, so that for this CR, these are the values of independent parameters that matches best with the observation. Now for those time period, for only that specific time period, take those values and forget about everything else. So with that, for each CR, we have stack of these images having a totally different set of values of the independent parameters. Because the problem is that we don't have this 2D map. We have just 1D. So we tried that also, but the model was struggling. It was overfitting for the server points, because it's totally wrong, right? You want 2D output, but putting a constraint only on few 1D coordinates. So it kind of overfitted those things. So that's why we wanted to do in the same manner. We tried very hard, but then we decided, okay. And with this, we are getting 100% accuracy, but it was overfitting. So that was the problem. So to have this 2D, if we want this 2D, we'll have to find the optimized version of this map, because this map is for any coordinate, right? So for a period, we try to optimize these values instead of this value and then make a 2D plot out of it. And then the model tries to learn that map, those optimized maps.
So they had to make their zebras in a sense.
Right, right,
That's
yeah.
how it
But I
works.
mean, I still think you could do it as the zebra generation problem, for lack of a better thing, right? Say you've got those image things there, and rather than doing the optimization, what you're using in the zebra generation is, okay, give me the optimized sets of these things, and then you could go and extract what you need out of it from there.
So that's what they,
But then again,
essentially, that's what they did.
It's a two-step process because you need the target first. So that's what the first step is to generate the target where you want to create the zebra you want to create. Once you have those, the network is effectively a image to image generation. So you think it's two images and you generate another image.
Yeah.
I mean, you need to know what you're
It
saying.
was a dumb question. I fall back on my
Actually subtle.
first question there.
It is, no, it's a good question because it's subtle how they had to make their own training maps essentially. But then it's exactly what you said, that once you have your training maps, you just say, these two images should map to this image, and you train a neural network.
Yeah, the subtle point is that ground truth map that's consistent with WSA.
Yes.
Because otherwise you can say not generate any 2D map for which the earth line point by Omni are correct.
Yeah.
They would be rubbish everywhere else. It would optimum. That's where it was saying it will overfit on the sun earth line on L1. It can be perfect, not according to Omni data. Everything else can be rubbish because you don't have all of the other information doesn't go into your cost functions. They can literally try, and that's what we're saying, what we're seeing.
And it's not a dumb question, by the way. I spent more than a month in first approach. Then we had a discussion and we thought, why we are not doing in this way? Because this can be useful.
Have you looked at all the experiments?
No, so we haven't done the multi vantage point or these validations. Now that's the next follow-up target. So use different heights apart from the ecliptic plane, PSP, solar orbital, stereo, all those things, and then see how they are performing in that way as compared to the default WSA. So not done, will be done.
It's another dumb question then, because I don't have any education on this topic. That WSA equation, I understand that the inputs are those two quantities that you get from SFI,
PFS.
from extrapolations.
Yeah.
And there's a velocity that is measured. Let me put the equation back. Okay, I can see alpha and I can see beta. Those are the two maps. What is V min and V max?
Yeah. So this is the WSA speed,
That's at 0.1.
and this is the expansion factor, FS,
Oh, FS.
and this D is the minimum distance from the coronal boundary.
So what other constraints do you have there that are observational other than FS and D? Everything else is fitted parameters.
Yes.
And the
Well, it's even
same
worse
for an
operationally,
entire,
it's just assumed parameters.
they're assumed parameters. No, I understand that's semi-empirical, but they're all identical for the entire CR.
Yes.
That's all I wanted to ask. I just
Yeah.
for my.
And actually, there is a very good question coming out from this is that, so these are the set of independent parameters, and this D and FS is a 2D thing, so coordinates. So why we are expecting that these values will remain the same at all the latitudes? The polar regions
Yeah.
can have different set of values,
Yeah.
but we don't have anything to check it. So that's why it is only relying on server points. And by the way, we use this everything because the ideology was not to forget anything. So this is almost 20-year-old relation.
Yeah.
So we wanted to use every information that we have. So that's why, so that we can make it more interpretable and so that we can rely on it, that how it is giving this value. So that kind of thing.
Yes, one of the biggest advances of this over the current method is literally the forecasters use those values for everything.
Yeah.
They just fix them, and that's WSA has been running with those for years.
Optimize them.
They don't at all.
Not
only that, they
it's always the same except for the input.
Yeah, and then
Okay.
not only that, they multiply the input magnetogram map by
2 or
two
whatever.
or three
Yeah.
before they actually put it in, just because they know it's
Right.
not right. So it's right now it's very ad hoc.
Yes.
Okay, thank you.
Yeah.
Yeah,
there was a figure you showed where you showed your skill score, the cycle. Following up on what you just saying, is that skill score relative to the WSA operational standard, or is it just relative to data only?
I didn't understand what the fit score was either. How does
So, okay, so let me define the fit score. That's what the referee was also saying.
You've revealed yourself, huh?
I was a co-author. I should know it because I'm a co-author.
So traditionally, to compare two time series plots, we use root mean square error, mean absolute error, Pearson correlation coefficient, or dynamic time warp. So we have these four things. Mainly, everyone is relying on this, either one or two or on everything. So what we thought, if we want to give one number, maybe we can use all four, normalize them, and get one number from 0 to 1. And that is what we are calling fit score. 1/4 plus summation of these. So it's just the quarter of the summation of all these one. So now we have a number which is coming from all these four from 0 to 1. And now your question is that, what was the question?
Well, okay, so the things you're comparing to get those four things are, you're comparing your predicted speed to your measured speed?
With yes, with the
Yeah, I guess what I was asking, well, so if you put the WSA operational model into this framework, what would its fit score look like?
okay.
Because I was wondering how you did compare to that.
Okay.
Because if there's this,
But WSA Enlil or WSA?
well, that's a good question. Or you're just doing straight up WSA?
Yeah, so I think it's
WSA plus X. So it's
So you're doing WSA plus, but you're not doing an HD model. I would compare it to WSA because that's the equivalent.
Yeah.
And so just to see how you do better compared to that, because what I'm wondering is, does this solar cycle effect show up in that?
okay. So your question is that this plot is for WSA plus comparison with the Omni or with the
Omni, yeah,
observation.
yeah.
But where is the WSA default comparison?
Exactly.
Yeah, that plot is missing. That is not there, but the value is there. For WSA is 0.51, the average of everything. And for WSA plus is 0.71.
So have you looked at that plot? I know it's not there, but have you looked at, because what I'm wondering is there a solar cycle variation?
Yeah. I think there is a solar cycle variation in the same way as this.
Right.
Because on average, the PCC remains the same. And this same variation can be seen everywhere on all the plots. However, they are very crude way of fitting with the polynomial fitting of order 5 or 6. But you can see the same pattern. The gray one is the WSA plus, but blue is also behaving in the same manner.
Is it worse than maximum or minimum or decline? When is it worst?
Yeah, so that's where we are struggling. What we found is that the model is performing poorest during the declining phase, starting from the maxima till going here. But I got the comment from Lisa when I was in a conference that instead of plotting the sunspot number, plot the polar field strength. They have some kind of lag. So then this region will match with the peak of that.
There's another possibility that I'm thinking of, which is related probably to what Lisa's talking about. But I know that Pete Riley did a study where he talked about how when you're near solar minimum and you've got a pretty flat heliospheric current sheet, it's really easy to fall out of that because all you have to do is move a little bit and you're out of the heliospheric current sheet, your speed goes crazy. Actually, at solar maximum, it's a little easier to fit because your model can be off a little bit and you'll still be in a fast wind stream or whatever. And I wonder if that, I mean, so I'm just looking at this paper because I wonder if that effect, how that relates to declining versus minimum. I thought it was more right at minimum, so maybe it's not related to this, but.
Yeah, I think in most of the studies, like there are two notions. One is that this whole framework is just relying on the open field lines, and the magnetograms relatively perform bad in the active this maxima. PFSs will perform poorly in maxima, hence this pipeline will perform poorly in maxima. Another is that if you are in minima, this dead region, even then the performance is poor of this. This has been seen. But my argument is that people only rely on PCC for those conclusions. And that's a big mistake. People should use all these four or more about the dynamic time warping. So it's more about the metric. If you use different metric, different conclusions can come in one study. So that's always there. But yeah, we know that in maxima and in minima, there are many papers which claims that, but we didn't find any such thing. This is, and it's very clear feature, right? You can see it is going up, coming down, going up, but only of 1.5 solar cycle. But I think I need to plot the polar free strength. And if that matches nicely, then we can make any conclusion from there.
So the WSA fit score in your table in the previous plot, can you go back one slide, please? Was 0.71.
Yeah, WSA is 0.51.
51. Okay, so you want a higher fit score. So
Yes, higher fit score. Yes. So green is good, yellow is fair, and red is bad. Very arbitrary. So I'm still struggling with the question, what's the perfect metric? And for that, I have one idea, and we'll have to see that whether it's working nicely or not. The idea is this. So it's so bad. So sometimes what happens is that we can miss this peak in WS. It can happen. We have this peak, but we don't have this. So any metric which is not knowing this information that we have missed one peak can have totally different thing. So instead of that, we can have dynamic time warping, which measures this distance like this, but of a fixed window. So we can fix a window and then compute the dynamic time warping distance, and then in a normalized sense. So this window, this window, this window, this window in some sense. So it will be dynamic window DTW. I don't know how to do it. Maybe one way is that have the number of local maxima and minima, then find the duration of that, and then provide that as a window.
yeah, I mean,
Try to find the scissor paper. We did a whole stuff on this, the metric analysis there, and I'm trying to find the detail on it. I'll see if I can get it for you. Sorry, Tommy.
for those who don't know, SISM was the program that operationalized the WSA in-law program in like 2010-11 timeframe. They were the ones that took it from a research model to an operating model at SWPC. They did a lot of work on verification, validation. So that was going to be my comment. This is validation of the model. Another way to quantify the success of the model is to put it into active forecasting mode and verify the forecast. How well does it predict the future?
Mm-hmm.
And just forget about how well it replicates the past. I mean, so that's always a good distinction to make. Model validation is not the same thing as forecast verification.
Yes.
And in an application like forecasting, the latter is more important in a sense. It's always nice to know how well your model did on postcasting, but forecasting is really the challenge.
Yeah. Yes.
But that means you got to get it operational and don't touch it and just let it run for a year and see how it does, or a solar cycle, ideally. So it takes a little
It
longer.
would be very cheap to put operational
Yeah.
sets, because again, WSA Plus is cheap, and then you can do hacks on top of it. You don't need to do anything.
Yes.
And they
Yeah.
will be literally running seconds.
Yeah, I mean, SWPC would do well to do that. Just have it in a parallel mode.
ECMC, there's scoreboard system set up, you put it in there.
So do they have one score?
They have a Sullivan scoreboard. They have an SCP scoreboard.
The CME arrival time, SCPs, and
Maybe they don't have solar wind.
solar cycle, I think, but not solar wind.
They were talking about solar wind, but
But we have
Thermosphere.
one challenge coming up.
there's a
So,
challenge.
Yeah.
Machine learning challenge.
Yeah. No, I mean, I mean, the other thing to do would be to put it on the Space Weather Track website.
Yeah.
Just run it like the live DST.
And can we advocate to use this WSA Plus in SWPC? Is it possible?
You can. It's difficult to get things operationalized there. It's because for them, operation means it's really been through a lot of hoops and
You should start by doing a cloak in there.
Start doing what?
Go get a cloak in there if you haven't yet.
so that can help. That can help. But
Okay, any more questions?
Afterwards, I can give you the reference for the paper here.
Any more questions from online? If not, let's thank our speaker again.